Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we continue with consistency, one of the properties that important for our estimator. So consistency, if you remember in applied statistics course, we have a variance very small, okay, or converge with certain value which is very small. So definition 9.2, the estimator theta head n is said to be consistent estimator of theta if for any positive number of epsilon, okay, the limit n goes to infinity will equal with 1. Okay, that's mean theta head n minus theta. This one will be less than equal with epsilon, then it will converge to 1. Or theta head n minus theta greater than epsilon value, and that is converged to 0. So by theorem 9.1, an unbiased estimator theta head n for theta is a consistent estimator of theta if the limit variance theta head n when n goes to infinity converge to 0. So for proving for this theorem 9.1, okay, you can see that if you have y is any random variable, so you have expected y equal to mu and expected variance y equal to sigma square, and this is less than infinity. And if k is any non-negative constant, so if you remember Chebyshev theorem, we will have this theorem. Okay, where is it? Probability y minus mu greater than k theta. This one is less than equal with 1 over k square. Okay, so k is a constant, theta is a standard deviation for population. Alright, so because theta head n is unbiased estimator for theta, okay, from the theorem it's given, or it said that theta head n is unbiased estimator for theta. So we have expected theta n head will equal with theta. Okay, and then let sigma theta head n equal with square root variance theta head n. Okay, this one clear. If you have variance theta head n, it will be v theta head n square lah. But this one, because it's a standard deviation, so it will be square root. Okay, it's a standard error of the estimators theta head n. And then we apply the Chebyshev theorem for the random variable theta head n. Then we will have this one. Okay, so here you can see that instead of y, we have theta head n minus theta. Okay, because we have this one. Okay, this is y, and then we have mu. Okay, and then here greater than k theta head sigma n. Okay, so this is considered the standard error of the estimator, and then we have this one. So from the Chebyshev theorem, we just substitute this one, and then this one, and here. Okay, so actually this one we have from here, but that one is proving. So due to these properties and Chebyshev theorem, we get this one. Now let n be any fixed sample size. Okay, for any positive number of epsilon, we will have k equal to epsilon over theta sigma head n. Okay, it's a positive number. Okay, this one we let. Okay, we let n be any number or any fixed sample size. Okay, and then for any positive epsilon, okay, number, we will have k equal to this one. So application of Chebyshev theorem for this fixed n and this choice of k. Okay, you will have at first you have this one. Okay, you have this one, but then you substitute with epsilon here. Alright, then here will be theta head n minus theta. So this one actually epsilon equal with epsilon over theta over sigma theta head n, and then here you have sigma, and then this one is less than equal with 1 over k square. So k you substitute with this one, and then here when you simplify, you will get variance theta head n over epsilon square. Okay, from here to here you will get this one. Okay, try solve this one. Okay, to the left, to the right, and so on, then you will get here. And then thus for any fixed n, okay, you can see that this value is in between greater than 0 and less than this variance theta head n over epsilon square. So if this variance, okay, approximately this variance, okay, the n is approximately to infinity, it will give you 0, and we take the limit as n goes to infinity, the preceding sequence of the probability will give you this one. Okay, so let's say if you can see here, you take the limit for all. So from this equation, okay, take all limit for each, and then limit here 0. When n goes to infinity, this one becomes 0. But here when n goes to infinity, and then here n goes to infinity, you will get 0. Therefore, theta hat n is a consistent estimator for theta. Alright, so important here, you can see that when you give, when the variance sigma hat n, okay, the limit n goes to infinity will give you 0. That means that estimator is consistent. So if you look example 9.2, page 451, okay, let y1, y2, yn denote a random sample from distribution with mean mu, okay, and variance sigma square. So basically it's a, if you look here, it seems like a normal distribution, okay. Show that the y bar n equal with summation of yi over n is a consistent estimator of mu. So if you look here, they use y bar n because they want to consider, we calculate using sample of size n. Okay, so now how is the solution? So this is based on knowledge, previous knowledge that you have learned. Okay, some theorems, some knowledge that you have learned, that you've learned in this subject, okay, previous chapter. Sometimes you will, you will use, okay, use it in order to solve, okay. So if you look the solution here, okay, from the earlier chapter, you know already, okay, from central limit theorem actually, the sampling distribution, so the expected y bar n will give you mu, and the expected variance y bar n will give you sigma square over n. Okay, this one if you remember from previous video, the same chapter, okay, but at the early chapter, okay, you have this one. Because y bar n is unbiased for mu, and expected variance y bar n goes to 0 as n goes to infinity. So the theorem 9.1 established that y bar n is a consistent estimator of mu. Okay, so you can see the solution is very short. It's until here. If you understand that what is the expected y bar n equal to what, and then what is the expected variance y bar n equal to what, and then if you look here, when n goes to infinity, this variance will goes to 0, so it means it's consistent. Okay, so this is another solution or another explanation. Okay, equivalently we may say that y bar n converge in probability to mu. Okay, you can see when the n goes to infinity, the value converge to value mu or 0. Okay, so the fact that y bar n is consistent for mu or converge in probability to mu is sometimes referred to as a law of large number. Okay, law of large number, usually, you have done, we've mentioned this before in applied statistics, okay, but law of large number, how is it? Okay, it's provide theoretical justification for the averaging process employed by many experimenters to obtain precision, okay, precision in measurement. So for example, an experimenter may take the average of weight of many animals to obtain more precise estimate of the average weight of animal of this species. Alright, so the experimenter's feeling, a feeling confirmed by theorem 9.1, is that the average of many independently selected weight should be quite close to the true mean weight with high probability. So in other words, okay, let's say I want to see your student CGPA. Okay, for example, we have 10,000 students. Okay, let's say it's difficult for us to get all. Okay, so based on the law of large number, okay, if I have n sample equal to 100, okay, if I have more sample size, okay, I'll take more sample. So it will give you, or the value of average too will be approximately to true mean weight, or true mean CGPA. Okay, the concept of when the sample size is large enough, okay, when n goes to infinity, then it will give you, or will converge certain value which is close with the true value. Okay, all right, so next is theorem 9.2. Okay, but I think I will discuss this in the next video because there is a example here to be shown as well. Okay, so I will end this until example 9.2. We'll continue with theorem 9.2 in the next video. Thank you, class.